All right, good morning, everybody. My name is Tyler Ruggles. I'm a research scientist at Carnegie Science. And if you are listening to this pre-recorded video, that means that I have failed to connect to my computer this morning, and I'm very sorry about that, but we will continue. We can continue on with the presentation this way. I'm going to be sharing some research conducted by myself and David Farnham and Ken Caldera, also of Carnegie Science, as well as Nathan Lewis of Caltech. And we are interested in incorporating multiple years of weather data into models of deeply decarbonized energy systems, with the idea that incorporating more years of data is going to build systems that are robust against different sorts of wind and solar resource droughts and fluctuations which could cause problems in a reliable system. In the same way that engineers design structures to withstand a century or millennium scale flooding events, we are interested in building systems that will withstand infrequent and severe resource droughts. Incorporating wind and solar energy into electricity systems is an emerging challenge because of the variability which we have on multiple timescales, from sub-hourly to daily, seasonally, and even annually. The figure that you see on the right is showing you data from 36 years of weather records across the continental United States, and it's showing you how much wind or solar energy you could have produced every day if you had resources spread across the United States. And the solid lines show you the median value for every single day of that 36-year record, while the darker regions show you the inner quartile, and the lighter regions show you the minimum and maximum value for every day. And there's substantial variability here. And we want to be able to build a system that doesn't just withstand 1 year of data, it can withstand multiple years of data, because we're going to be living in the real world where every weather year is not the same as the following weather year. We are far from the first people in this space. I think a great quote from a recent paper by Zeringer et al. Is, power system design is highly sensitive to the interannual variability of weather, and planning based on a single year can lead to operational inadequacy and failure to meet long-term decarbonization objectives. On the right-hand side, you're seeing a figure from their paper where they ran their model on different years of input data. That's shown across the x-axis, and you can see the different built capacities in their model to supply their electricity load. They did have two different scenarios, where the darker bars are scenarios that are 50% powered by variable renewables, while the lighter bars are 80% powered by variable renewables. But the key point here is that different years will find different optimal capacities if modeled one at a time. With this idea, we ask, how many years of data is enough for reliable systems? We are interested in how models of idealized least cost electricity systems vary depending on the number of years of resource and demand data incorporated into the model, and as well as what are the implications for system planners. For example, if we had just 2 years of data records, where 1 year has a substantial solar drought with very little solar irradiance, 1 day or a couple days, then maybe that system is going to be favoring a wind-heavy mix to make it through those days with a solar drought. Where if the other year has a wind drought, that'll be favoring a solar-heavy mix. Now, if we model those 2 years together, we're going to be creating a system or optimizing a system that is robust against both of those years and could handle both types of that variability, hopefully in future years. So we specifically ask, how do system costs and asset capacities change based on the number of years of data incorporated into a model? Also, can we identify critical years with substantial leverage in determining asset capacities? And 3, how does the performance of modeled systems improve when incorporating more years of data? And to test that, we test on out-of-sample data. Now, I'm going to say a big thank you to Sally Benson, who previously gave us an introduction to macro scale energy modeling, that's exactly the space that we're operating in. We're not modeling electricity system distribution or anything near that detail. We're operating at a very high level where we're just dealing with asset capacities and hourly demand profiles, as well as wind and solar generation profiles. So we have a very simplified model. It's even simpler than what Sally was showing yesterday, where we have 3 different generation technologies: wind, solar, as well as a firm generation technology. In this presentation, you'll see me refer to that as natural gas with carbon capture and storage, but that could also be nuclear or some other zero energy fuel. We also have battery storage, and together those 4 technologies are going to be optimizing an electricity system to deliver a least cost system that supplies 100% of the electricity load. These assets all have fixed costs, and for the firm power, we have variable costs. The wind and solar profiles are based on historical weather data. So we looked at historical weather data from the regions of interest, where we reconstruct what wind and solar generation could have been had there been wind turbines and solar panels across in this region. The hourly electricity load, we use a mix of historical data, and then we also jump to using some synthetic data later in the presentation. We also have possible constraints that we can place on the total dispatch from firm power, and this allows us to explore different decarbonization thresholds. The decision variables in the model are the installed capacities and the hourly dispatch of each technology, and the goal is to supply electricity load as cheap as possible. So let's get to that first question. How do system costs and asset capacities change based on the number of years of data incorporated into a model? I'm going to begin with just the simplest system that we have, which is a firm generation-based system. This can be thought of as somewhat akin to our historical systems, where we had large thermal fleets and maybe some large hydro as well. And the electricity was essentially dispatchable. When you need electricity from a resource, or when you need power from a resource, it can provide that power. Clearly, some things have ramp rate constraints and some economical constraints, but in general, firm resources, when you need energy, it can be supplied. Now, if we think about optimizing a firm generation only system over 1 year of electricity data, it's going to build a system that can supply where the generation capacity exactly meets the peak electricity demand. But if you had, say, 17 years of historical ERCOT data, each of those 17 years has a slightly different peak. So you'd be building to different thresholds. Only if you optimized all 17 years together would you be guaranteed a solution which would have that very peak demand. If we look at the left little figure down here, this is the historical ERCOT, the historical hourly demand data from ERCOT, and you can see that there is some growth in this from economic expansion, population growth, probably among other factors. We detrended this data to make it much more comparable year to year to year, so that we are focusing on the variability in the data and not the growth in the demand profile. And with this in mind, let's show some initial, some simple results from this firm generation only scenario. I'm going to show a number of figures that look very similar to this. So let's go over the axes for a second. The x-axis is showing the number of years incorporated in each simulation. So we have an ensemble of results, and in that column with F1 on our x-axis, there are 17 different systems that are built based on the 17 different years of demand data. Once you go out to, say, 3 years, we are sampling at random from those 17 years of data. So we'll take 3 different years at random, and those years can actually repeat, and we optimize the system based on that. And what you see from that is that the built capacities for firm generation increase as you add more years of data. This is quite intuitive. As you sample more and more years of data, you're going to have you're going to have more higher peak years incorporated and be slowly asymptoting towards that maximum value. The y-axis here is, sorry. The y-axis here shows you the capacities, and I've shown you a number of different lines indicating trends in the data. So there's mean as well as median lines. The median lines, you'll see some stair-step kind of behavior at times. That's because there's only 17 discrete values that are available for this maximum capacity number. Where the mean kind of more smoothly trends upwards. I also showed the minimum and maximum values for the ensemble of results, as well as the inner quartile range is the shaded region. Now, once we get out to high numbers of years, this is a serious combinatorial problem. You could have millions and millions of different combinations. We do not run millions of combinations. We just start with the first 200 random combinations that we have and consider that our ensemble. So with more sampling, we could end up with maybe some smoother lines, but there is some randomness in this. Now let's look at the system costs for a more decarbonized system. So we're considering a wind and solar powered system with batteries. I'm showing this not because we think there will be systems that are 100% wind, solar, and battery, but to illustrate some points about selecting the years. So bear with me, I will get to some, I will incorporate the firm generation back in soon. So in this system, same x-axis, you'll see that it's more constrained now. I only have 4 years of data. That's what we are computationally limited to with our 1 hour time scale resolution is 5 years per simulation. And then you see on the y-axis, the system cost, the levelized cost of supplied energy, which is quite high. We're using current asset capacities based on the EIA. So in the future, in 25 years, we do expect these costs could likely come down. But again, we're trying to find trends in the data. We're not trying to predict the actual cost of a system. So this seems like a reasonable step. Now let's look at the asset capacities. Where the wind nameplate capacity is shown on the left, solar nameplate capacity in the middle, and storage on the right. And just to remind people, we're studying the ERCOT region in Texas. The wind capacity factors are about 40%, and the solar capacity factors are around 28 or 30%. So you can use that to convert nameplate capacity to other values. And one of the first things that you see is that the wind capacity actually decreases as you add more and more years into the simulations. This actually really shocked us at first. And in addition to that decreasing mean and median value, you see that there are some systems with next to zero installed wind capacity. So we're trying to think about why this could be, and our hypothesis was that there are a few years with severe wind droughts, and when you sample those years, you're going to build a system with minimal wind capacity because you need lots of solar and storage to make it through those droughts. And because of that, and with that, as you sample more and more years, you have a higher probability of sampling one of these wind drought events, which would lead to a low capacity. So with that in mind, let's step to question 2. To question 2, where can we identify critical years with substantial leverage in determining asset capacities? And now we're going to view those results, but instead of the number of years on the x-axis, we're going to look at each year individually as far as what systems, we're going to look at the results from each year individually. So the x-axis shows the individual years from that data record, and for a given year, let's say 2009, all the values in the 2009 column, those are simulations that included the year 2009 in them. So it'd be 2009 and 2012, 2009 and some other years. But if it had 2009, the value is included in this box and whisker plot where the whiskers go from 5 to 95%, and then we have flyers beyond that. And I'm specifically just showing simulations where there were 2 years of input data. So, and you can see there's a general kind of trend in the middle, or like a normal distribution from about 20 cents to maybe 23 cents per kilowatt hour. And then there's this 1 year, which is our incredible outlier, the year 2015. And if we go and look at the asset capacities for this year, where we're now showing the system cost upper left, solar upper right, wind bottom left, and storage in the lower right. If you look at this year 2015, you see that we built a very large amount of solar capacity. We built next to zero wind capacity, and we built a huge amount of storage capacity. All right, to better understand what was happening in year 2015, we conducted a little solar and wind resource drought analysis. And we took some methods from a recent paper where they defined a drought day as a day where the potential production from wind or solar power is 50% or more below the seasonal expectation. And from that, you can declare that a drought day. And they were interested in measuring both the length of these droughts, and that 50% definition defines a type of severity of the drought. So if we consider that our definition of a drought, we can look at the number of wind droughts in the ERCOT region over these 17 years of data. And many years, all the years had quite a few single day wind droughts. And all years even had a number of 1 to 2 day long drought events. And solar, there weren't quite as many droughts. But to understand exactly the severity that was really impacting our model, we went and looked at the records from year 2015 itself. And what we saw is there were about 2 days worth of hours, which had incredible leverage over the model. And when we looked at the wind production during those days, there were 2 days in a row with wind producing at less than 90% or 90% below its seasonal expectation. Just for this presentation, we define that as a severe drought day. And those 2 days were back to back. And over looking at all 17 years of our data, those 17 years of data, we saw that this was the only year that had 2 severe drought days back to back. A number of other years, actually only 4 of them, had single day long severe drought days. And from that, let's think about taking 2 more steps in this analysis. Let's try to model more years of data simultaneously to see if the trends kind of asymptote out or see what happens there. And let's also consider going beyond the 17 years of data to considering the whole 40-year data record that we have. We could even take a step towards longer data records in the future, but we haven't had time yet. So originally, I mentioned that we're limited to modeling 5 years simultaneously, and this is at 1 hour resolution. Now, if we take the steps of coarsening our resolution to 4 hours, we're able to include up to 20 years of simultaneous data. And in general, many modeling teams are really pushing for 1 hour or finer resolution when you're talking about a lot of wind and solar data. And we are on board with that. We're just taking a look. We're seeing if we can learn anything from this more coarse resolution and incorporating more years. And what we see is that the system costs, the mean values, the median values, they track very similarly between the 4 hour resolution and the 1 hour resolution. The wind values, they still have the same kind of trends. They're a little bit offset, maybe a little bit steeper decline for the 1 hour resolution. Solar appears very similar between the two, and storage is also fairly similar. With this, remember, we're not trying to model the exact future system. This is a macro energy model, and we've boiled away a lot of the complexity of the electricity system. We're trying to learn about fundamental system behaviors and making sure that these trends are going in the same direction and largely line up. That gives us confidence that we can at least learn something from this process. And our next thing to extend our records is to move beyond our historical ERCOT demand data and use some synthetic data. There was a recent analysis by Waite and Modi where they provided an algorithm to reconstruct a synthetic version of demand data based on the hourly temperature in any region. This is resolved down to the county level. They were looking at the prevalence of different types of electric appliances in areas. And with that, they could scale the demand based on the temperature there. So this is synthetic data. Demand data does not perfectly align with the historical demand data. However, it's reasonable. And what we see when we look at these system costs is they have largely the very similar shapes, but the synthetic demand data, the values are all kind of translated upwards, a little bit more costly. The wind are very similar. Solar, the trends are very similar and the lines are similar. It's the storage where the synthetic demand data has larger capacity when we use the synthetic data. But despite that, the curves are very similar. And the similarities here give us confidence to take this data and extend it over the 40 years so we can look at once in 40-year events in our model or in our study. And what we see right away when we take the step from looking at those original 17 years to looking at 40 years is that no longer does the wind capacity drop as we add more and more years of data. And that made us think that maybe that one year, 2015, really was like the worst possible wind year out of our records. And the solar trajectories, the storage trajectories, the system costs, they're all very similar. It's the wind which really changed as we added more years with different types of variability. Now let's look at some of those extra years that were added on, because there were some outlier years in those additional data years. Now I'm showing the system cost, these box plots again, where we show the effects of 1 year at a time. And the year 1983, 1989, and again 2015, these are the real outliers as far as system cost is concerned. And as you can predict, they also have outliers in some other capacities. So we have the solar capacities there, the wind, as well as the storage. Year 1983 was also a year that had a substantial wind drought. Interestingly, year 1989 was a wind drought year, but the day right before this drought event had a huge surplus of wind. And that's why you see wind capacity built in 1989, but you see a phenomenal amount of storage built there. So let's summarize what we've kind of learned from this simplified wind solar battery system. And yes, that's not what we anticipate anyone will actually install, but this teaches us stuff. For a 100% reliable wind and solar battery system, the least cost system can be essentially determined by one or a few weather events. And years with these critical weather events can be identified a number of different ways. They can be found as the outliers in these box plots, in the system costs or the capacities. Analysis of the drought events can also provide some information. And now let's add in what Sally Benson referred to as clean, firm power, and add a little bit more flexibility and dependability into our system. And what we see here is that all of a sudden our system costs, our wind capacity and solar capacity become much less variable year to year, and as we add more years of data. Now we limited the firm generation to 5% of the annual electricity load, and this was just a way to kind of ratchet and like adjust a specific deep decarbonization threshold. You could choose a different value here. We tested a number of them and we saw that the results were very similar, but they would scale these lines either up or down, translate the lines up or down. Now, so wind and solar, the mean and median values stay pretty flat as we add more and more years of data. Wind and solar are being used to provide the bulk of the power in the systems, while if we look over to the right, we have storage increasing a little bit as we add more years and deal with more variability, but really it's the firm generation that really expands as we add more years of data and more variability into each of the simulations. The firm generation is the is the reliability like backbone of this system. And just to return to these figures, let's see if the ability to add firm generation removed these outliers in the capacities. And we'll focus again on those three kind of outlier years, years that were previously outliers. And we see that two out of the three have incredible outlier values as far as the installed capacity of firm generation. And we can also, while their solar values are located largely in the bulk of the distribution, same with wind and storage as well. It's the natural gas capacity, which is significantly above the bulk of the distribution for these two events. And what happened in these two events is they coupled a wind drought with a large cold snap, which really increased the electricity demand. These both occurred in December of their respective years. Is this unique to the ERCOT region in Texas? Absolutely not. I advertised France in the abstract and haven't had much time to touch on it, but I just wanted to show some results with 10 years of data from France. And we do see that there are years with significantly less installed wind capacity compared to the other years, and wind solar battery system. And once we add that firm power as well, these outliers still exist. So even with firm power, we can have some outlier events, and we learn that by studying multiple years of data. Now let's take a quick look at how the performance of these modeled systems improves with this additional data. To test this, we take all of our simulations and we hold the capacities fixed, and we run them on different years of resource and demand data. And we let the system optimize the dispatch during those years, but we don't let the system change the capacities in any way. And what you see immediately is that there are large reductions in lost load going from 1 year of data to 2 years to 3 years of data incorporated in the models. And this is largely driven by avoiding models that only have an easy year of data in them. As soon as you incorporate more years, more and more years, you are more guaranteed that there'll be at least like one reasonable sized drought that will force you to build a system that can withstand future droughts. And striving to produce a 100% long-term reliable system without some form of reserve margin is going to be very, very difficult. Reserve margin is a concept in current electricity system planning and operations, where you take whatever your forecasted peak demand is, or peak system performance, and you say, let's build a system that supplies like 15%, can supply 15% more power than we think. You could apply that here, where, and with what we've done here, we know which technologies to target in a least cost system. We should target the ones that really provide the reliability. So in the wind solar battery system, we should probably be targeting solar and batteries, at least in ERCOT. Those would have more reliable performance than wind. And when we go to, once we add firm generation, that's really the one where we're going to get a lot of value from adding a reserve margin or excess capacity. It's adding more capacity in our wind and solar. Those are the resources which have the drought. So to really build a long-term reliable system, focus on the part which can give you that firm generation. So in summary, incorporating more years of data into electricity system optimization models on average increases system costs, it increases the system reliability, and it can yield trade-offs where certain technology capacities are expanded, while others remain approximately constant or even decrease, depending on what years of weather data you have. And with this analysis, we can identify which technologies provide that reliable portion of a reliable system. Now, many energy models cannot incorporate, or more detailed power system models cannot incorporate multiple years of data. So we don't anticipate people using 10 years of data simultaneously. What we think could be beneficial, though, is having analyses like these that identified the kind of critical problem years, or the years that had a lot of leverage over built systems when we had our hour-long simulations. And those would be good years to test your models on. Or if you're going to, if you could optimize on just a single year, you could include that year and see how it would change the optimization results in your model. So with that, I'd like to thank the symposium conveners, all of our great participants for making this fun and engaging, as well as thank our energy system modeling team at Carnegie Science, Caltech, and UC Irvine. And thank you also to Gates Ventures Inc. for a generous gift, which provided funding for this work. And as this is pre-recorded, please feel free to email me with questions or comments. Thank you.